Okay, thank you, everyone. I've been walking the floor today, and it was pretty exciting to see all the startups that are actually bringing innovation to the automotive space. I've been attending EcoMotion for the past good 4 years, and it's really good to see how this evolution of startups, new startups, supporting the ecosystem of automotive. And Nvidia is basically a startup. It's a 13,000 person startup. And like any of you here in the room, we basically look for innovation. We look to develop the things that are impossible to develop. And this is how we started with the first gaming infrastructure and became a leader in gaming, developing high-performance GPUs. And then took the same GPU and moved it to the artificial intelligence and become a leader in artificial intelligence, using those high-performance GPUs in data centers and having many of the cloud providers running on this artificial intelligence, even when you are not aware of. And then we have decided to approach one of the markets, I would say the most challenging market, the most ambitious project that we will see in our lifetime, and this is developing an autonomous vehicle. Essentially, all cars will be autonomous. All vehicles will be autonomous, if it's a car, taxi, shuttle bus, public transportation, industrial vehicle. And most of them gather the same type of challenges. First, you need to understand how to perceive the environment that you are approaching. How do you deal with a school bus? How do you deal with a police driver? Or how do you deal with different type of weather? These challenges, or perceiving the environment, are challenges that we see across the board, regardless what type of vehicle or autonomous vehicle we will develop. So when you look at all these challenges, when you're looking at the environment, we need to first understand in an autonomous vehicle what is around us, what is in the environment, perceive the environment first, and then making a decision upon it. And then after we make decision, we need to actually predict the next step, because actually making the decision, the next step decision, is not sufficient. And then after we make the next step or prediction, we need to localize ourselves in the environment, provide HD mapping, actually run training while we're driving, and localize ourselves. And all this requires high-performance AI computing. You cannot achieve and solve all these type of challenges without an actual AI car. And what that means? It means that you need a supercomputer in the data center, and you need a supercomputer in the car. Supercomputer in the data center will be used to train those neural networks. While you're actually receiving all the data, train the system, and basically develop a model, a very accurate model, that then needs to be used in the supercomputer in the car. So Nvidia basically developed a DGX platform with 1 teraflops and 2 teraflops in the data center, and we developed a supercomputer in the car named Pegasus, and we'll talk about this later. The third pillar is simulation, and we'll touch with this a little bit later on in the presentation. But in order to be able to predict all this type of different scenarios and situation and edge cases, we have to develop some type of a simulation. And last but not least is safety. Throughout the process of developing autonomous car, you have to follow certain regulation or certain safety aspect, from designing the chip to writing the architecture, developing the software stack, validating it, and even writing documentation. It all has to comply with automotive regulation. So it has to be ISO 26262 compliant, and has to be ASIL B and D compliant. And that's part of developing an autonomous car. You don't want to get a car on the road while it's not fully compliant. you want to save people's life. So when we look at Nvidia as a company, we have developed a massive perception database. What we do is we partner with ecosystem partners for perception, if it's LiDAR, radar, cameras, and so on and so forth. We actually develop this and we train the system. We gather hours and hours of data, and we actually label it within Nvidia. We have more than 1,000 employees today that actually, the only thing they're doing in life is labeling all the data that we are receiving from the perception. And this actually to enable and tune the model, to have the model, to perfect the model before we actually download it or compile it into the car. After we actually develop the train model, what we do is we run it through validation. And the validation is a process that goes through a simulation and run through simulation to different type of situation that then are being tested with the test cases. And then, and only after we train the model, simulate it, only then we actually get the car on the road. So let's take a step back and talk a little bit about how neural networks work and how difficult it is today to perform even the easiest task of understanding a single video frame. So when you have a single video frame, you have to break it into pixels. When you break it into pixels, you have to look at multiple pixels or group of pixels actually grouped into object. And you look at objects in the car that it can be a car handle, can be a tire, can be a wheel, and then you group those objects into an image. And then you look at this image and you can classify it as a car or something else. And when you classify it as a car, you can then classify it as Audi A7. To achieve that, you have to go through a very long training in order to be able to identify and to fine-tune the neural network. So practically, neural network is not programmable. Neural network is the data write the software. It's not people that writing the software, and that's key. So when we actually got the neural network to work, and we're driving the vehicle, the neural network basically do some image classification, sign classification, object classification, lane classification. And here is an example that you see the bounding table, the bounding blocks around the people. It actually can signify or indicate between people, signs, pedestrian, and so on and so forth. And you can look at this as a pixel level, so higher resolution pixel level in order, again, to identify and classify what is the barrier or what is the object that you're looking at. And then the car can make a decision either to go straight, make a stop, make a right turn, make a left turn. So when you look at the car itself or the supercomputer in the car, you have multiple networks running in parallel. You have object network, you have free space, distance, sign detection, weather detection, and all this together, LiDAR and path perception, all this together needs to run in parallel in the car. Because it's not enough that you have sensor fusion for LiDAR perception or image perception. If you drive in a different type of weather, you need to identify what weather it is and then to switch accordingly. So all networks needs to run in parallel. And that consumes a lot of performance. So you need to have a very, very large computer or supercomputer in the car. So we went through the neural network basic, and we understand that we need to do training to all these type of different networks. But when we look at that, how long will it take us really to train an autonomous vehicle to be able to safely get on the road? When we look at all this data, we came up to 20 cars from a fleet, for a regular fleet, will drive together 1 million miles a year. Now, when we look at the US statistics, you see that there is 770 accidents happening in 1 billion miles. So only after you actually train 1 billion miles, you can detect 770 accidents. Is that enough for you to safely to put a car on the road? How about 2 billion? How about 3 billion? How about 5 billion? So it's actually more than 10 billion miles required really to go over all the different test cases. That's massive training. That will take decades if we just take car and drive them. This is exactly the reason we came up with Constellation. Drive Constellation is a way for us to be able to put supercomputer in the data center and create a virtual world. Basically create a simulation world of the world of us. And we have very large experience with rendering, with gaming. Put this together with AI, and you can produce maybe the best simulation out there. And together, we actually put another supercomputer to get the simulation input as a car. This is basically the Pegasus, which are car supercomputer, and then it perceived what happened outside. And it perceived what happened outside, and any actuation that this Pegasus takes, or the in-car computer, you drive back into the simulation. So you have what we call hardware in the loop. With this hardware in the loop, what you need to do is, let's first create the environment. What type of environment are we? For example, blinding sun is one of the key barriers for lidars and for cameras. So if you just drive 24 hours a day, guess what? You get about 5 minutes of blind sun a day. We can actually simulate blinding sun 24 hours a day. So we can simulate this blinding sun from different angles. We can actually create even things that cannot be created in reality, which is moving the sun horizontally versus vertically. After we create the environment, we then come back to the car and look for optimization of the sensor location. So we actually move the sensor position to be able to produce the best result. So and we take this together and we tested them. So when you actually have the simulation output and you can move the sensor location, you can then test and find out the best location for the sensor. You can go then to the OEM and look for different type of sensor location to be able to improve performance. Here you see actually our drive sim, which are our Constellation output, and this is where you see the input for the supercomputer. We have another way to simulate it, what we call person in the loop. Person in the loop is a person that is actually driving it, basically like gaming, and be able to drive recklessly. So you can actually simulate a person under the influence, or a person that drives recklessly, and this is how you can get your test case to corner cases. This is the Ferrari that is driven by a person. So as you can see here, you can see here 4 different cameras, front view, rear view, side mirrors, and you can actually test all these different scenarios. You can test this in day, you can test it at night, and actually have different lighting, so you can have photorealistic output of this simulation. This is where the hardware in the loop, what I mentioned, the actual car supercomputer, produce labeling and classification of what they see as an input. So we talked about training, we talked about simulation. Let's talk for a second about the platform, the actual in-car supercomputer. I want to invite an Nvidia veteran to join us here, Ophir Zamir, to actually show us the evolution of the different hardware within Nvidia only in the last year and a half. So what you see in Ophir left hand, which is here, this is a PX2 platform that was developed only a year and a half ago. This PX2 platform has basically our prior Volta architecture, a prior Pascal architecture with a Parker device, and it supports 24 TOPS. All this platform here is basically got here into what we call the Xavier device, which is this device that you see here. So basically, in a year and a half, we converted a complete platform that back then, a year and a half ago, was the best platform or the highest performance platform available in that footprint. We got it into a Xavier. So now we have 200 watt, basically, with 24 TOPS into a 30 watt, 30 TOPS. With this Pegasus, we actually can perform today with 2 Xavier and 2 Volta, we can actually perform 320 TOPS. And this type of supercomputer, this is what you need in the car to get from level 2, all the way to level 5. And one key thing about this is that this platform now supports functional safety. So this platform, as defined before, support the ISO 26262 as well as the ASIL D. This is a massive disruption in the industry, and this is how innovative Nvidia is. Basically defeating Moore's law. Thank you very much, Ophir. I have 2 more slides. Oops. Please, 2 more slides. Okay, so one more sentence. We basically have more than 370 partners worldwide, Tier 1 automotive OEM, LiDAR partner, radar partner, map planning, and of course startup like we have here in Israel. We sometimes invest in startup, sometimes acquire startups, but almost what we need and what we're looking for is to move startup and help them to complete development using our platform that you've just seen today. We have an inception program that we offer to startups to join a program, and that allows them to have access to all the Tier 1 and OEM database that we have. And last but not least, we have a GTC in October 18, which will basically enable a lot of the startup to come to see everything at the GTC environment, which is Nvidia worldwide convention, and we have only about 6 of these worldwide, and one of them is in Israel in October 18. So we look forward to see all of you. Thank you.